So one, was it?
Go ahead.
Do you have a homework question or?
Oh, is that where we're going?
No, we can do homework first, yeah. I don't know if anyone looked at it yet.
I did have a couple, is that right?
Yes, shoot, let's go.
So, for number 4B.
Which is that one? Sorry, I never remember the
Oh,
numbers.
yeah. So that's the one where we're making the TXY curve.
Okay.
And so, like I've got this algorithm that I got out of the book, right? You pick a trial bubble pressure,
Mhm.
bubble temperature, and then you compute Y using Antoine's equation and Raoult's law, right?
Mm-hmm.
And then if Y is too large, if the sum of all the Y's of all the vapor mole fractions is more than 1, then you reduce the temperature, right? And the other way around, you increase it if it's too low. So when I was doing that,
Yeah.
I was having a really, I'd start at like 75C and it would kind of go up and start to converge to a certain temperature, but then my algorithm would oscillate. Like it would never actually converge on an actual, temperature.
Mm-hmm.
And so it made it so that my bubble curve was really jagged. So do you have any tricks to like how to make those like a really
Yeah, so no disrespect to Professor Sandler, but he may be giving you an algorithm from the era of slide rules.
Yeah.
And not from the era of computers. So here's my system. So let's say, for example, we're doing, I don't know, do or bubble, it doesn't actually matter. So if we do the bubble curve, right, we're gonna start off with, this is our kind of governing equation. We know our x is because that's what you're fixing, right? So you wanna know what the bubble pressure is and what the dew pressure is for a given set of scenarios. So let's get here.
This is for the temperature. I already did the pressure one, but.
Same equation.
Oh, really? Oh.
Exact same pressure. Remember, these equations are good for all circumstances of vapor-liquid equilibrium. Now, the only thing that makes them powerful for the bubble and the dew is the assumption of whether or not we know what the liquid composition is or whether we know what the vapor composition is. Since you're creating the curve, you have ultimate authority to do whatever you like, right? So, in the bubble curve, this is an explicit equation. I have a temperature, I have Anton's equation, I can get the vapor pressure, I know what my composition is, boom, I get my pressure. Now, in the case of a temperature TXY diagram for the dew and the bubble points, it's just the opposite. It's still one equation, one unknown, but it's now an implicit equation, right? Exactly the same way as solving a cubic equation of state for density. So in this case, what we're doing then is we fix our pressure. Let's just do the bubble curve. So we have x of A times P of A plus 1 minus x of A, P, B star of T. Right, we know A, we know A. Now the only thing is we don't know what the vapor pressures are, but in this case here, right, we can imagine that we substitute this expression into here. Now we still have one equation and one unknown. One equation, pressure is known, composition is known, A is known, B is known, C is known, T is unknown, X is known, A is known, B is known, C is known. So all you have to do is a goal seek. In Excel, for example, right? So all you do is, in Excel, I would have temperature equals blank. Now with any nonlinear solver, you have to give it an initial guess. So just throw something out there. As long as it's reasonable, Excel should converge. So let's say 20C, right? Then just tell Excel, now what I always do here is I move this to the other side of the equation. 0 is equal to this minus P. So when this equation is equal to 0, that means you satisfied the one equation, one unknown criteria. You have your temperature of the bubble point. Exactly the same formulation for the dew curve. Now, the other thing to note in Excel is that if you're trying to solve for a TXY diagram, this is somewhat tedious, right? Because you're basically going, vary this, do this, get the temperature, copy to the table. Vary this, do this, copy this, do it, put to the table. So instead, what you'd rather do is build this up, right, let's say we call this bubble equation, right? So this is a cell right here where you input this long equation based on information being fed from that cell. So if you use Excel's solver, who's used Excel solver for a system of equations? Okay, so a few. So when you go into solver, has everyone used solver at least once? Who's never used Excel solver before? Have you used Excel's goal seek?
Yes.
Okay, so goal seek is for one-on-one. Solver, you can do a lot more. So in solver, it's got this criteria where it says like objective, right? So it's like set this cell equal to, let's say 0. And anytime you do nonlinear solving, in MATLAB, it forces you to do this, always set it equal to 0. Because with any equation, it's trivial to move everything to one side of the equation and say good enough, right? So the objective is some cell, and then in Excel it says set to, I always put 0. I want to make my life easy. I don't like remembering things. And then it says by changing some other cell, right? This is exactly like goal seek so far. Now the only difference in solver is that this can be a range of cells. So you can use solver to do multivariable curve fitting. But in this case here, what you'd want to do is you would want to change all of the temperatures. So rather here you have Z of I, P bubble, P do equation, right? And you'd actually have another one, T here. So this is T bubble, this is T do. So you'll have to do this twice, right? So you have your Z, you change your bubble, satisfy this equation, change your T, satisfy this equation. That's your bubble temperature, do temperature. Does that make sense?
Mm-hmm.
So then what you do in Excel is you can add constraints. So when you solve this the first time, you're going to say, I want to set this first cell here to be equal to, so that's this star here is this star here. Set this one equal to be 0 by changing all of these cells, right? But then what you want to do is you want to add in the constraints such that all of these other ones equal 0, right? And you could do it as a series. Basically say drag and drop all of these. And then Excel's solver is smart enough, right? So how these things tend to work is MATLAB and nonlinear solvers, what they do is they take your initial guess and they increase it a little bit and they decrease it a little bit. And they check to see which of these cells respond. And then it repeats the process here. And then it repeats the process here. Right? And it knows how much I change my unknown variable, which functions are going to be changing. And so Excel, in the blink of an eye, right, because computers can do billions of calculations a second, in the blink of an eye, Excel is going to know, oh, duh, this equation only affects this one, this equation only affects this one, this equation only affects this one, and so on and so forth down the line. And then it'll just basically do the whole thing in one go for you. Does that make sense?
Yeah. Thanks.
Any other questions, Mason?
So let's see, I had another one. Oh yeah, so on 4C, for that one, we're trying to find just an XY diagram, right?
Mm-hmm.
And we're doing it at a constant pressure instead of at a constant temperature.
Correct.
So how do we find the vapor pressure if we don't know what the temperature is? Like, or how do we find the temperature at every point, basically, so we can find the vapor pressure?
In the so what you'll be doing is you'll be taking your results of the TXY diagram and just plotting your X's versus your Y's.
So that will give us our temperatures
Yeah.
in each composition at a constant pressure.
So in the XY diagram, the temperature will be varying, but you won't know what that temperature is.
Yeah, okay.
So, but just know that it does change. So if you have an XY diagram and a TXY diagram, based on a certain XY composition, you can know what the temperature is at that point.
Okay.
But when you create your plot, you'll be basically just cross-plotting, you know. This one's a little bit trickier, so actually what you do instead, I'd have to go back and think of the shortcut ways, but basically what you'll do is you'll take like this temperature here, which will correspond, in this case this is the bubble, this will be your X, and then you'll take some other temperature here and go over here, and that'll be your Y, but you'll want to make sure that these temperatures are the same. I have to go back and double check my solutions about how we do that trivially.
Okay, but like the outcome of this part of the problem will help with that part then, is basically what you're saying.
Oh yes.
Okay.
So you'll probably have to reconstruct your TXY diagram so that your temperatures are constant. Otherwise you can't create your XY curve. Because let's say for example, you discretize your Z 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. That doesn't guarantee that at some temperature your bubble curve is going to have the same temperature as your do curve. because you've discretized it differently. But once you know your bubble and dew maximum and minimum temperatures, then you can repeat that calculation, but by knowing the temperature and making sure that the pressure is equal. So you can solve for X for a given temperature and a given pressure. And then you can use that to solve for Y, and then you create your XY diagram.
Okay. Thank you.
All right.
I had one question.
Yes.
On problem 1, the final solution has a 2 in front of the entire thing.
Yeah, so that one, I'll be totally honest, I had to like hit the books to figure out, because that's the integration of that infinite summation.
Okay, I had it as 1/2, because I thought we were counting each of those B, I, J twice, so I had to divide it by 2 to only count it once. So I thought it was like P over 2.
So on that one there, I don't have a good reason other than that's how the math works out. And I believe I had to look up that integration to know what the integration of that infinite series was, and that was the approach. So yeah, I don't have the perfect answer for that particular scenario, unfortunately.
I'm gonna try to figure that out.
But I think you have to have that factor of 2 and that integration in order for to get the equation. And I think I went back and I verified and double checked with other sources, and that was appropriate. But okay, I tried. Any other questions? So, as a general rule, from this point onwards in your careers, it's very important that you guys become familiar with computational tools. Because modern sort of engineering is reliant on the fact that you can solve lots of problems very quickly. So, if once you have one equation, one unknown, as long as it's in some sort of a coherent form, I want you to absolutely resist the urge to play with it any further and just throw it into a computer. That's my general rule, particularly for thermo, because a lot of the problems that we're going to be doing from this point onwards, Mahmoud and I are cooking up a particularly aggressive computational problem. We'll see if we can get it out for next homework. But effectively using the Peng-Robinson to solve for partial fugacities in vapor-liquid equilibrium. So it's basically like the vapor pressure problem on steroids. So if you are brand new, starting out, never programmed, my recommendation is Python. I don't know Python, so I can't help you too much, but it's pretty dang close to a lot of other simulation tools like MATLAB. And it's free, and everyone uses it. So Python is going to be a really great resource. If you're going to learn, get Python and use it. Because in mass transfer next semester, you will be mandated to use Python aggressively. So if you think the math is hard in this class, just wait till mass transfer. Would you agree, Mahmoud? Okay.
The problem will be hard.
You will not be able to, you can't physically solve them without Python. You can't solve systems and partial differential equations on the back of your hand.
Well,
you cannot.
I got a pretty big hand.
All right, so that was a fun little side discussion on all sorts of things, homework and equations of state. Let's go back to low pressure vapor-liquid equilibrium. I was hoping to get through liquid-liquid equilibrium today. I don't think it's going to happen. I had some videos. I have a video of boiling water, which we'll see how it's relevant. Never would you have thought that boiling water would be interesting. And I will try my best to make it interesting, probably on Monday. So in low pressure vapor-liquid equilibrium, as we've sort of uncovered based on the questions for the homework, PXY diagrams are way easier to generate than TXY diagrams. The reason behind that is because for Raoult's law system, PXY is an explicit expression. For TXY temperature dependencies, it's always going to be nonlinear, right? And it's going to be a nonlinear equation that we can't rearrange to solve trivially. Now the reason why the TXY is nonlinear is just based on the Clapeyron equation. Yeah, I believe it's the Clapeyron equation. Vapor pressure is exponentially dependent on temperature. That's a base root fundamental conclusion of just basic phase equilibrium. So, we'll talk about low pressure vapor equilibrium more or less from a temperature being constant standpoint. The other reasoning behind that, is because activity coefficient models are really difficult to tune. It takes a lot of data, it's very expensive. So there are still labs that exist that charge hundreds of thousands of dollars to generate phase equilibria diagrams for companies that are doing big industrial processes, right? So what they'll do is they'll do, vapor-liquid equilibrium, fit it to parameters, repeat it as a function of temperature, and go on from there, right? But getting good activity coefficient data as a function of temperature is also kind of a pain. But just note that all the equations that we'll be doing are exactly the same. Everything's the same. It's just easier to do it from a PXY perspective. So in the case here of a standard PXY diagram, the bubble curve is just going to be a weighted average. I'll do P, Z, and A. I'll do A and B. So this is going to be the vapor pressure of A at whatever the system temperature is here. This is going to be the vapor pressure of B at whatever the system temperature is. Now, the lazy man's way of generating the full phase diagram is to first calculate the bubble curve, right? We're going from the liquid phase to the vapor phase. Liquid is where we're going to have most all the non-ideality. So what we do then is once we know a condition, so at this point right here, I know my composition, I know my pressure, and I know my temperature, which means I have a fully defined system. The only thing that I need to relate here, which is my liquid composition, to a vapor composition, is that my partial fugacities are equal. So in the simplest case, that's Raoult's law. So in Raoult's law, I want to relate my liquid properties, right? This is my partial fugacity for the liquid phase for species A. I want to relate it to my vapor phase. This is my partial fugacity in the vapor phase. That's the model that we've chosen. Now what we'll be talking about today is when it's slightly more complicated. In this case, we're only considering ideality and non-ideality in the liquid phase, and if we consider a ideal gas vapor phase, then we have a relationship. So if we start from the liquid, we know our composition, because we're totally there, we just made it. We have an activity coefficient model. If we don't have an activity coefficient model, we would have to actually have the vapor composition as well. So if you have the liquid composition and the vapor composition, you can calculate the activity coefficient. But in this case, for the simplest perspective, we have the liquid composition, we have our activity coefficient, we know our pure species properties. There's no way you can do any multi-component mixture stuff if you don't know your pure species properties. It's just a waste of time, it's too complicated. And you know your system pressure, because you're in the lab. You're the one controlling the nitrogen tank. You know exactly how much pressure you're putting on it. Which means that we can directly solve for the vapor mole fraction, which allows us then to draw a line over here, and we can construct a dew curve by repeating this process over and over again, and then we simply connect the dots and we have our dew curve.
Will it be a bubble curve?
This is the bubble curve here. So once we calculate the bubble curve, then we go through and do the dew curve. So the bubble curve in this case here, we can calculate using this equation right here. Now this is not the bubble equation until the liquid composition is equal to the total composition. This is just any equation you can pull off the shelf and use for any circumstances you want for vapor-liquid equilibrium. Right? It becomes the bubble curve when we combine it with the fact that we know the total composition. So what we talked about, okay, is this clear, what we're doing here? So what we talked about on Wednesday was looking at non-ideal vapor-liquid equilibrium, and the non-ideality is on the liquid phase. So in this case here, we have, bubble curve. A bubble curve where the activity coefficient is equal to 1. That means it's a weighted average. In this case here, we get rid of this here. Mole fraction times by the vapor pressure, that's just a weighted average. So it should be a straight line connecting the vapor pressure of pure A to the vapor pressure of pure B. Now if the fluids don't like each other, right, at high pressures we have a liquid, If the fluids don't like each other and there's non-ideality in the liquid phase, they want to get away as fast as possible, meaning that you're going to have positive deviation from Raoult's law behavior. This is going to be activity coefficient is greater than 1. Now, if activity coefficient is greater than 1, that means that the excess Gibbs of the system is going to be greater than 0. Low Gibbs means happy fluids. High Gibbs means unhappy fluids. Minimum Gibbs is the objective. If you have fluids that really like each other, they're okay hanging out. They'll stay liquid as long as you like. Right? These systems do exist. Positive excess Gibbs is going to be the default in the world. If I graph any two random chemicals that have ever been created, the default is probably going to be the fluids don't like each other. But that doesn't necessarily lend itself to interesting chemistry. So most of the fluids that we actually look at, some of them will exhibit negative excess Gibbs because, well, those are the fun ones that are interesting, that we can manipulate more easily. So if the activity coefficient is less than 1, that means that the excess Gibbs is less than 0. Now recall, the excess property is the difference between the mixing and the ideal mixing. The reason why we have to do this is because entropy always increases when you mix two fluids. A throwback to when we first introduced multi-component systems. Now, let's say hypothetically, we have a scenario where the two fluids either really don't like each other or really like each other. And we find a position right here where we observe that the change in the pressure of the phase transition as a function of the mole fraction is equal to 0. So we each reach a maxima or a minima in a PXY or a TXY diagram. Does anyone know what this causes?
It's an azeotrope.
It is an azeotrope. So I'm not going to go through the math, but let's say, for example, we take the pressure of a low pressure, non-ideal vapor-liquid equilibrium. We take the function right? We want to see what is the consequence of observing a maxima or a minima in the PXY diagram. So just as an exercise, which properties here, and let's draw this out actually. So let's do this for a binary system. So XA, activity coefficient of A, vapor pressure of A, plus B, activity coefficient of B, vapor pressure B. Excuse me. As an exercise, so we don't have to go through the mathematics, but just as a thought sort of experiment, which of these properties are dependent on the composition? So, X of A, is it dependent?
Yes.
Of course. Activity coefficient of A?
Yes.
Yes. Vapor pressure of A?
No.
No, it's a pure system property. B?
Yes.
Activity coefficient of B?
Yes.
Vapor pressure of B?
No.
No. So that means there's going to be a whole lot of product rules in this derivative, right? This times this, this times this, this times this, this times this, right? So it's a lot of math. The ultimate equation is that if this equation equals to 0, which is equal to this expression up here, well, actually rather, we take the partial derivative with respect to x of A or x of B, works out the same, right? If we evaluate this derivative, set it equal to 0, work out the mathematics, work out the calculus, what we will find, oh, we also have to use the Gibbs-Duhem equation, so that's one right there. What we will find is that, in this case here, my nomenclature is 1 and 2 as opposed to A and B, so I'll switch over to this so I don't mess up my notes. This is what the mathematical conclusion will be. If you set it equal to 0, you do all the math, everything works out. The Gibbs-Duhem equation, just as a sort of a cliff note, will relate the fact that I don't remember if it's plus, minus, times divide, whatever the case is here. But the fact that these two terms will cancel out according to the Gibbs-Duhem equation. Yeah, I can't remember if it's how exactly the coefficients are, if there's a log in there, whatever the case is. Oh, actually, I do have it in my notes right here. It's right from x1 dln activity coefficient 1. Yeah. From the Gibbs-Duhem equation. So remember, the Gibbs-Duhem equation is just like saying that the mole fractions add up to 1. Because remember, the way that we defined partial molar properties is somewhat arbitrary, so we can't independently vary them. So the Gibbs-Duhem equation is the consequence that we can't independently vary the activity coefficient of 1 and the activity coefficient of 2. They have to vary in the same way. So if these two expressions are equivalent for a binary system, so they cancel out, that throws into all this mess. Okay, so this is our conclusion. The activity coefficient of species 1 times by its vapor pressure is the same as the activity coefficient of species 2 times by its vapor pressure at the position where you have a maximum or a minimum in either the pxy, the dew curve, or the bubble curve. So, why does this matter? So let's evaluate the consequences of it and demonstrate how this gives us an azeotrope. So if we are to take our vapor-liquid equilibrium expression, we have we rearrange this, the activity coefficient of I times by the vapor pressure, which is this expression here, is equal to. Okay. Now, if we apply this for both species 1 and species 2 in a binary system, we will find that y1p over x1. Pressures cancel out. We have the criteria that y1 plus y2 is equal to 1. Mole fractions in the liquid phase are equal to 1. So if we consider all of these constraints, the only solution to this equation is that the mole fraction of the liquid is equal to the mole fraction of the vapor. So why do we care about azeotropes?
Make your separation tough.
They make it more than tough.
Expensive.
Make it impossible.
They make it
Well,
impossible.
Not impossible, you just gotta get creative.
You gotta write.
Well, you have to break the azeotrope.
Yeah.
Without breaking the azeotrope, you cannot separate two components with distillation. Right, so let's do a really quick experiment on this one, or a little quick example. So what this is saying is that if I have a liquid of a particular composition, and I boil it at the azeotrope, I'm going to create a vapor at exactly the same composition. So what an azeotrope is effectively doing is it's treating all of the two-component, multi-phase, multi-component equilibrium, and it's behaving like a single component. So if we look at our yx diagram, or xy diagram, we have our line here. This is our y equals x line. So for a normal material, right, it looks something like this. And we counted out the equilibrium stages. We go 1, 2, 3, 4 stages, and we can do the separation. But in the case of an azeotropic system, we're going to have a condition where x is equal to y, which means that we're going to fall on this line. Now what happens then is that normally, so let's think about this, right? We typically draw all of our diagrams based on the more volatile species. So if I choose some arbitrary composition here, let's say a 50% liquid mixture, the vapor phase is going to be higher than 50%, because X is the more volatile species. And that's a nice convenient way so that all these diagrams look the same. So every time we look up a diagram, it's not a 100% new scenario. So if I choose a starting point right here, where I have a liquid composition of 50%, should my vapor be higher or lower than 50%? Right, because it's the more volatile species, it's going to be higher. The more volatile species wants to get away. And exactly that's the case here, right? This is obviously above the y is equal to x curve. Now if I have an azeotrope where my x is equal to y, my liquid composition is equal to my vapor composition, that means that I'm no longer going to have a nice looking curve. It's going to go up, cross, and then go underneath. Now the consequence is that if I were to count out distillation stages, right? 1 stage, 2 stage, 3, 4, 5, 6, 7, right? You can never cross that line. So it doesn't matter how many stages you try and use, you're never going to be able to purify your compound beyond the azeotropic composition. So in this case here, we would call this the ZAZ, the azeotropic composition. You're never going to be able to get past there. Now, the next kind of interesting thing is that if we were to start off with a mixture up here, let's say this is 80% volatile species, you get less than 80%. So meaning on the other side of the azeotrope, the fluid is behaving somewhat weirdly. The more volatile species all of a sudden becomes the less volatile species. And this is all due to the multi-component nature of the system, right? Because when you have, for example, an azeotrope and lots of non-ideality, right? So same example here on the PXY diagram, right? If I go up here, right, you can see that as I add more of the volatile species, it wants to boil less. Now, typically how that's going to happen is when you have a mixture of A and B. So in this case here, I have a lot of A and a little bit of B. Activity coefficients are the largest in dilute systems. So the activity coefficient of A in this picture is going to be approaching, 1, not 0, 1, right? There's so much A, it doesn't even know that B is in the system, right? It's not a big deal. Yeah, we can handle a little bit of a multi-component property. In the case of B, it's going to go to some finite value, which is the activity coefficient at infinite dilution, which is going to be the highest typically, right? Because it's your one molecule of B surrounded by a sea of people that aren't your friends, okay? So what happens then is normally, maybe B is a really non-volatile heavy species, but he's so unhappy to be in a party of all A molecules that it just wants to get out of there as soon as possible. So even though A may be the more volatile species, in fact, it's going to be B that is going to be preferentially leaving, actually no, the liquid phase, be this way, right? B is going to be really wanting to get out of that liquid phase. And this contributes to the non-ideality of the system. All right, so we talked about this a little bit already, but how this translates, so the PXY is where the calculations are by far easier to do. Well, actually, yeah, PXY, the calculations are easier to do, but they're harder to do experimentally. It's typically going to be easier to control the temperature than it is the pressure. So the reason, if we look at a TXY diagram, this is just how azeotropes are typically defined, is on a TXY. We're going to call both of these the bubble curve, just to differentiate. This is not a bubble and a dew curve. These are two different bubble curves. They call this one a maximum temperature azeotrope, and they call this one a minimum temperature azeotrope. And this is sort of the conventional way that you call azeotropes. So, which of these two is more common? Let's not answer it. Let's walk it through step by step. High temperature, what phase are you in? Vapor. Low temperature? Liquid. Okay. So I'm a liquid, and I'm getting heated up. So the first one that I encounter here would be potentially a minimum temperature azeotrope. So that means I'm boiling at a lower temperature than I would normally do if I were an ideal mixture. So this one's going to be more common, So in the minimum temperature azeotrope, is my activity coefficient greater than 1 or less than 1 for each species, on average? It's going to be greater than 1. For a maximum temperature azeotrope, your activity coefficient is going to be less than 1 because they're hanging on, they're actually having a really good time, and they're okay being a liquid mixture. And it takes a lot higher temperature to boil those two out. So one other thing that's very useful at azeotropic compositions is we can use them to benchmark activity coefficient models. So if we look at modified Raoult's law, at an azeotrope, the liquid composition is exactly the same as the vapor composition, meaning that the mole fraction in the liquid phase is equal to the mole fraction in the vapor phase. So we can use that to knock off a couple of terms, in which case our activity coefficient at the azeotrope is just equal to the system pressure divided by the vapor pressure of the pure component. So if you have an activity coefficient, if you have an azeotrope for a binary system, you can automatically tune a two species or two component activity coefficient model like that, right? Because I have this equation here for species 1, I have this equation for species 2, which means I have two unknowns. So then what I can do is I have an activity coefficient model that requires two coefficients, the Wilson equation, for example, the Van Laar equation. Those are two species, two variable activity coefficient models. I can explicitly calculate what those coefficients have to be in order to predict the azeotrope position and composition. Does that make sense? So with azeotropes, so is that a no? Does that make sense?
It's a bit more complicated because the activity is a function of temperature and the preset is a function of temperature, so you have to assume temperature.
Yes, but at the pressure and temperature of the azeotrope, for example. So for example, if we have a particular azeotrope right here, right, and the TXY, again, that's why it's not trivial to do so, so rather it's easier to do it here. Right, so with the pressure, for the temperature being constant, this is where you would tune the azeotrope, so tune the activity coefficient model. But, okay, so here's the kicker. When I change the pressure, right, in thermal, all variables are connected to all other variables. So if I change the temperature, the properties change. If I change the pressure, the properties change. So by the letter of the law, my activity coefficient is also going to be a function of temperature, pressure, and composition. But the good news is that liquids really don't care about pressure changes that much. So the approximation that we use is that the activity coefficient isn't going to vary with pressure significantly. Whereas for the temperature, unfortunately, it does quite a lot. But you can estimate how the activity coefficient varies with temperature by looking at heat of mixing. The activity coefficient is related to heat of mixing properties. Partial excess enthalpy relates how the activity coefficient changes as a function of temperature. Now I used to cover that, but it's just a lot of math. So if you look in your Sandler book, you'll be able to see. Well, this is not the one thing I didn't want to erase. Okay, so an azeotrope ruins your day. Well, it depends actually. An azeotrope makes your day if you're trying to tune an activity coefficient model, but it ruins your day if you're trying to actually do the separation. So how do we break an azeotrope? So one way is you can actually turn a binary system into a ternary system. So you can use an azeotrope breaker that changes the vapor-liquid equilibrium, but then it adds in an additional downstream separation that you have to do to remove your azeotrope breaking compound. The easier option is to use two distillation columns. So, how we do this, let me draw back my XY diagram. We will have a feed So let's say, for example, our feed composition is somewhere in the left-hand side of our XY diagram, meaning we're going to be below the azeotrope composition with respect to component 1 in the system. Now, if this is our bottoms composition, we can go 1 stage, 2 stages, 3 stages. In fact, let me redraw this a little bit. I'm exaggerating it. That's not how they typically look like. What they typically will look like is something more like this. So 1 stage, 2 stages, 3, 4, 5, 6, 7, 8, whatever. Can't get past the azeotrope. So what we'll do is we'll vary the pressure. Now what effect this has is due to the Clapeyron equation. In this case, this is the Clausius-Clapeyron equation, so we're assuming ideal gas behavior. So what this is doing is by varying the pressure of your distillation column 1 to your distillation column 2, what we're doing is we're effectively changing the temperature of operation of those distillation columns, right? Because, of course, temperature and pressure are linked to vapor equilibrium. If I change the pressure, I have to change the temperature, because that's how it's going to change. You can boil water by lowering its pressure or heating it up. Everyone's in agreement? So, even if at the composition here, where we reach our azeotrope, the properties of fluid 1 and fluid 2 just end up hitting this nexus where they form an azeotrope. However, their pure fluid properties are not going to be constant as a function of temperature, right? Unless their critical points are exactly the same, basically. Their relative volatility or their heat of vaporization is going to be different. As you get closer and closer to your critical point, your delta H of vaporization gets closer and closer to 0. So the sensitivity of how much your pure fluid vapor pressure changes as a function of temperature is going to be a function of how close or far away you are to your critical point. So for any fluids, just because you hit this perfect little nexus of properties that you form an azeotrope, it's unlikely that that's going to persist for all temperature pressure conditions. Right? So the fact that the heat of vaporization is related to the vapor pressure, and the heat of vaporization is related to how close you are to the critical point and your cohesive energy, changing the pressure is going to shift your azeotrope composition a little bit to the left or a little bit to the right and change its composition slightly. So the objective then, in doing a pressure swing approach to breaking an azeotrope, grab a different color, is that in your first column, if you can distill it to very near to your azeotrope, what you need to do is shift the azeotrope enough that you pop out on the other side. The more of a pressure swing that you do, the more you'll move the azeotrope. But the more pressure swing you have to do involves changing the pressure significantly in your process flow stream. The less pressure swing you have to do, the more stages you have to have in each of your columns in order to break that azeotrope. Right, so it's an engineering problem. There's the reason why chemical engineers get paid a lot of money, right? So the objective then is you want to shift your azeotrope so that it is now on the other side of your XY diagram. And then you can continue your separation 1, 2, 3, 4, 5 stages on the other side. Note that the procedure that we've used here on the opposite side of the XY diagram is exactly the same. Right? My design rule is still my x equals y line. My equilibrium is always going to have to be on my actual equilibrium curve. The procedure is the same, it's just upside down. And that's how you can count out the number of stages on the second distillation column to break the azeotrope. All right, is there anything else to cover? So on Monday, we will talk about liquid-liquid equilibrium, and beyond liquid-liquid equilibrium, we will be discussing the effect of nucleation, and other mechanisms of phase transition. So based on the curvature of Gibbs free energy, whether or not you have a pseudo-stable fluid or an unstable fluid, it'll tell you how those two things phase separate. Has anyone ever heard of the term spinodal decomposition? So spinodal decomposition is a phase transition mechanism of an unstable fluid. And it's exploited quite often in making high surface area composite materials. So if you're trying to make some sort of a capacitor or a supercapacitor out of polymers, or you want to have some sort of integrated network where you have charge transfer, let's say for example in a organic electronic device or organic photovoltaic, you want these polymers to separate following a mechanism of spinodal decomposition. And I'll show some simulation videos of what that looks like. But based on the properties of the Gibbs energy, it'll actually tell you how the phase transition will occur, right? Which is sort of a unique circumstance of thermo. Thermo usually never talks about the mechanism of these transitions, but this is one area where it does. So where thermo informs the kinetics. But usually, thermo and kinetic processes are separated at birth, and they never interact. But this is one area where they do, which is kind of nice. Have a good weekend. Watch the football game, and I'll see you all on Monday.